Okay, the last thing we're going to be covering today is fluids. I'm not even going to try and pronounce this guy's name. This guy's law. The law can be used to find the pressure difference when talking about a liquid flowing through a constantly sized pipe, like for example, a straw or your lung alveoli. Okay, so we use this formula, delta P equals 8 mu LQ over pi r to the fourth, where L is the length of the pipe, Q is the flow rate, R is the radius of the pipe, and mu is the viscosity, and P is delta change in pressure, right? And there's a lot of variables, and usually you won't have to like do all of these because this is a lot of math. Usually what they might ask you something like that is if you like double the length of the pipe, but you make it, but you have its the radius of the pipe, how would that change the change in pressure? And then you would know that 1/2 would be to the fourth, whereas this would only be doubled, so it would you have to just do the math there. Okay. And like the answer would be like, it would be like 30 times bigger, like 10 times bigger, like 2 times bigger, 4 times bigger, 2 times smaller, something like that. Okay, and that's just like an example. All right, next we want to talk about laminar versus turbulent flow. What we typically think of for fluid flow is called laminar flow. And when I say typically think of, I mean in terms of physics. In terms of real life, we actually mostly know liquid flow as turbulent flow rather than laminar flow. And I'll show you an example in a bit. Laminar flow is when all of the fluid flows in a parallel lines with no flow just kind of disrupting each other. The fluid in the center flows the fastest and slows to get to the edges. I'll show you a diagram of what this looks like, but think of this like a flock of birds flying orderly together in like a V formation. So the liquid is kind of going in a V formation, and all of like the particles of water are staying in their own lane and kind of just going in a straight line, and they're all parallel to each other as well as parallel to the pipe. Okay. However, in real life at faster velocities or in other cases, like the ones that typically occur when you open your faucet, you actually get turbulent flow instead of laminar flow, which is chaotic and disorderly. And this is what I mean when I say in real life, you probably know turbulent flow. When you open up your faucet, the water that comes out is turbulent, it's not laminar. Turbulent flow is chaotic and disorderly. There is a lot of perpendicular movement and mixing between the lanes. This is more like a chaotic highway when there's like a lot of traffic. There's cars merging, changing lanes, cutting each other off constantly. It's kind of like very chaotic. It's not staying in a line. This is kind of what it looks like. So remember, laminar flow is kind of like the V shape, right? And each of these like a line of water molecules going straight, whereas turbulent flow has a lot of these like twisting and kind of like doing this and that, right? And there's like mixing and nothing is like orderly. Okay. And like I said, when you see, we'll be mostly working with laminar flow in physics, but in real life, actually most flow that you see is probably turbulent. If you opened your faucet and instead of turbulent flow, which is what water normally looks like, laminar flow would look like this, right? This water is actually supposed to be like moving, but you can't even see that it's flowing. It just looks very clear and very orderly, and that's because it's moving laminarly. Okay, this is what water would look like out of a laminar faucet. So let's talk about in our bodies. Generally in our bodies, blood flows laminarly. However, there are certain conditions in which it becomes turbulent. An important value to know is the Reynolds number. A high Reynolds number, usually about more than 2,300, is usually turbulent, while anything lower is laminar. Note Reynolds number is unitless because all the units cancel out. And the equation for Reynolds number is RE equals rho V D over mu. V is velocity, D is diameter, rho is density. Don't get confused with the D's. One is density, the other is diameter. And mu is viscosity of the liquid. Our blood vessels typically have a very low diameter, so the D is very low. And because that Reynolds number is also usually fairly low, and you get mostly laminar flow because the Reynolds number is low. In things like sometimes in our aorta, which is like thicker, you may get turbulent flow in that one area. right? And like there's a lot of research going into this, and there's like a lot of like models, like mathematical models and stuff that are being used to like show like the different change in flow and everything. You don't have to know that. I just know Reynolds number is important. This is the equation for it, which is important to know. Usually our body is laminar, sometimes turbulent. Okay. And that's it for today's lecture. I know there's a lot of things that we covered, from circulatory system, flow, these different laws, coefficients, thermodynamics, a lot of stuff we covered. So, but this hopefully helped fill in the gaps that were missing from our 15-week program when we talked about thermodynamics, mechanics, and liquids and gases and circulatory system, things like that. Hopefully this kind of helped give you some clarifications on some stuff, okay?